In the Planning and Designing section, we'll take a look at the principles involved in planning and designing cloud infrastructure. You'll learn how the AWS well-architected framework is used in planning and designing. We'll take a look at scaling and all the different versions. We'll look at the importance of loose coupling, how you can build redundancy into your cloud infrastructure, how you can save money by cost optimization. We'll look at automation and how it can make management of an IT environment easier, and also we'll take a look at security and how you can secure your cloud resources. So let's start with scalability. In the past, you would have to estimate the peak load of your systems and purchase your hardware accordingly. So perhaps you were setting up a new website and you were estimating that you were going to get 1 million people per month hitting your website, so you buy the hardware accordingly. But then you find out that only 50,000 people are hitting it, or 10 million people are hitting it, so your hardware is inappropriate for the work. Cloud computing provides virtually unlimited on-demand capacity, so you can scale whenever you need to. To do this, your designs need to be able to seamlessly take advantage of these resources. And there are two ways to scale, vertically and horizontally. Vertical scaling means increasing the specifications of an individual resource. For example, increasing the memory or the number of CPUs on a server. With AWS, this is easily achieved with a restart of your virtual server, so that it resizes to a larger or smaller instance type. The advantage of this approach is that it's very easy and requires little thought in the short term. However, this type of scaling can eventually hit a limit and sometimes be cost inefficient, especially if you scale up to some very large instances. Horizontal scaling means increasing the number of resources rather than the specifications of each individual resource. For example, adding additional web servers to help spread the load of traffic hitting your application. This is a great way to build applications that leverage the elasticity of cloud computing. However, not all architectures can distribute their workload to multiple resources. A stateless application is one that needs no knowledge of previous interaction and stores no session information. An example of this would be a web server that provides the same web page to any end user. A stateless application can scale horizontally as any request from any end user can be serviced by any of the available compute resources. You can add more resources as required and then remove them when the capacity is no longer available. Stateless applications do not need to be aware of their peers. All that is required is a way to distribute the end user sessions to them. And there are two ways to distribute load to multiple nodes. The first of these is the push model. A load balancer, such as the AWS Elastic Load Balancer, is a popular way to distribute a workload across multiple resources. An alternative, but less recommended approach, is to implement a DNS round robin using Amazon Route 53, where DNS responses return an IP address from a list of valid hosts in a round robin fashion. This is an easy to set up option, but it can cause issues if DNS records are cached. The alternative to the push model is the pull model. Tasks that need to be performed can be stored as messages in a queue, and multiple compute resources can pull and process the messages in a distributed fashion. Examples of this are big data processing scenarios, where many servers work to analyze data and return results, or media file conversion processes, where multiple servers convert the files as they arrive. Amazon SQS or Amazon Kinesis are services that can provide pull model load balancing. Most applications need to maintain some kind of state information. For example, an automated multi-step process will also need to track previous activity to decide what its next action should be. You can make components in your architecture stateless by not storing anything on the local file system, and instead storing user or session-based information in a database, like DynamoDB or MySQL, or on shared storage, like Amazon S3 or EFS. Additionally, Amazon SWF can be used to centrally store execution history and make your workload stateless. So the opposite of stateless applications are stateful applications, as it's not possible to turn some layers of your architecture into stateless components. For example, databases which are stateful by definition, or applications that were designed to run on a single server. Providing multiple users a consistent view of the database or application is much simpler when your components are not distributed. Distributing the load is possible, though, through session affinity. This means that all transactions of a session are bound to a specific compute resource. However, this means that existing sessions would not be able to utilize newly introduced compute nodes. And also, if a node is shut down or becomes unavailable, users bound to that session will be disconnected. For situations when you need to process large amounts of data, it's always beneficial to see if a distributed processing approach can be used. Imagine a task that requires a huge amount of data processing. If it was to run on a single compute resource, it would max out the resources and take a long time to complete. If you can divide the task into smaller fragments of work, then each of the tasks can be executed across a larger set of compute resources. Examples of this are the AWS Elastic MapReduce service, which allows you to run Hadoop workloads across multiple EC2 instances, or Amazon Kinesis allows you to run multiple shards of data on EC2 or Lambda resources for real-time processing of streaming data. The concept of disposable resources is completely new with cloud computing, as cloud computing completely changes the mindset of an IT infrastructure environment. Traditional environments involved purchasing hardware up front and required manual configuration of the software, network, etc. Whereas with cloud computing, all infrastructure is temporary or disposable. You can launch new instances when you need them and get rid of them when you are done. Automate compute resource initiation is a way to speed up the creation of new environments. AWS has plenty of features to make new environment creation an automated and repeatable process. And there's 3 options available which we'll look at in the coming slides: bootstrapping, golden images, and a hybrid approach. Bootstrapping means you can take a newly launched AWS resource with its default configuration and then execute automated scripts to install software or copy data to bring that resource to a required state. So you could launch an EC2 instance and copy data on so that it becomes a web server. Scripts can be parameterized so that different environments, production or development, can be initiated easily. With AWS, bootstrapping can be achieved with your own scripts, Chef or Puppet, OpsWork, lifecycle events, or CloudFormation. Golden images mean you take snapshots of your EC2 instances or RDS instances or even EBS volumes, and they can be used to launch new instances. These EC2 instances can also be customized and saved as AMIs, Amazon Machine Images, and then you can launch as many instances as you want from this template. If you have an on-premise virtualized environment, you can also use AWS VM Import-Export to create your own AWS AMIs. The hybrid approach makes use of both bootstrapping and golden images. You can launch new instances from a golden image, but then bootstrap to configure other actions. Basically, with AWS, you are only restricted by your imagination or coding skills. AWS assets are programmable, so you can apply all these techniques and principles that we've just talked about to entire environments and not just individual resources, so you can completely rethink the way you work your IT infrastructure. Automation is a big part of planning and designing cloud infrastructure. AWS allows you to reduce the level of manual interaction in your environment. Using automation, you can react to a variety of events without having to do anything. Let's take a look at some examples. AWS Elastic Beanstalk. Developers can upload their code and the Beanstalk service automatically handles resource provisioning, auto-scaling, load balancing, and monitoring. EC2 Auto Recovery. In some situations, you can use auto recovery to automatically recover an EC2 instance if it becomes impaired. The recovered instance is identical to the original, instance name, IP address, metadata, etc. Auto-scaling. You can automatically add resources to cope with demand spikes and decrease again during quiet times. CloudWatch alarms and events. CloudWatch can send SNS notifications to alert when a particular event occurs. For example, CPU usage is too high. the notifications can be used to perform follow-up actions, like run a Lambda function. Opsworks lifecycle events. You can continually update your instance's configuration to adapt to environment changes. For example, if a new database instance is added to your environment, then an event can automatically trigger a chef recipe that points existing applications to the new server. Loose coupling is an important concept. Applications should be designed so that they're broken into smaller, loosely coupled components. The desired outcome is that a failure in one component should not cause other components to fail. This is achieved through a variety of measures. Firstly, well-defined interfaces. By ensuring that all components only interact with each other through specific technology-agnostic interfaces, for example RESTful APIs, will result in being able to modify resources without affecting other components. Amazon API Gateway is a fully managed service for APIs, which you can do this with. Loose coupling needs services to be able to interact with each other without having any prior knowledge of their existence. For example, imagine two servers communicating on hard-coded IP addresses. Then the addition or modification of resources will result in manual interaction to update the configuration. However, loosely coupled infrastructure is an essential ingredient in making the most of cloud computing elasticity. The easiest way to achieve this is to use an elastic load balancer service to provide a stable endpoint for all your services. This way, they don't have to worry about each other, the elastic load balancer does that for them. Rather than use synchronous integration, where server A completes an action and passes it to server B, which then passes it to server C, asynchronous integration involves the use of an intermediate storage area, like an SQS queue. This approach means that when a server A completes its action, it sends a notification to SQS. This way the compute resources are decoupled and not directly linked to each other. This means you can easily add or remove resources without having to update the configuration of the existing compute resources. Designing applications to fail gracefully allows other resources to continue a service without causing a complete outage. Examples of this would be if your primary website fails, the Route 53 DNS failover feature points your users to a backup site hosted on a static website on Amazon S3. The idea is to continue to provide a service, even if it isn't the full experience. Traditional IT infrastructure involves developing, managing, and operating applications with a wide variety of underlying technology components. AWS isn't just about EC2 instances. There are a suite of products to do everything mentioned and a lot more besides, to help you lower your IT costs and allow you to move faster as an organization. For example, managed services. AWS provides many services that are fully managed: databases, machine learning, analytics, search, email, etc. This lessens the burden on your IT infrastructure department. RDS databases mean you don't have to worry about backups, fault tolerance for your simple databases. S3 allows you to store as much data as you need without having to concern yourself with capacity management. Serverless architectures. You can reduce operational complexity of your applications through the use of serverless architectures. Tools such as the Internet of Things, Lambda, S3, Beanstalk all allow you to run your applications without paying for any server infrastructure. In a traditional IT environment, the type of database in use is typically restricted by constraints on licensing, support capabilities, hardware availability, and things like that. AWS provides you with multiple managed database server options that remove these constraints, meaning that you can choose exactly the right database for your needs rather than making use of what is available to you. AWS offers fully managed, easy scalable services for relational databases, NoSQL, data warehouses, and search functions that provide fully managed, easily scalable services that can create synchronously replicated standby instances in different availability zones. And they'll also automatically fail over without the need for manual intervention. We'll cover databases in a whole lesson later on in this course. Now we'll take a look at redundancy. Introducing redundancy will ensure your systems are highly available, so they can withstand the failure of individual or multiple components, for example hard disks, servers, or network links. Introducing redundancy will remove single points of failure from your systems. This is achieved by having multiple resources for the same tasks in either standby or active mode. Standby redundancy is often used for stateful components like databases. The standby resource becomes the primary resource by it failing over to it. The standby resource can be brought online only when required to save cost, or it can already be running to speed up the failover process and minimize the outage. Active redundancy is where multiple redundant compute resources share requests and are able to absorb the loss of one or more of the instances failing. Examples of this would be multiple web servers sitting behind a load balancer. Automatic failure detection allows you to react to an outage automatically without the need for manual intervention. Services like Elastic Load Balancer and Route 53 let you configure health checks so you can automatically route traffic to healthy resources. For example, setting up a health check to test for a HTTP 200 response, which means OK, would allow AWS to know if a node is healthy or not. Services such as OpsWorks, Elastic Load Balancer, and EC2 Auto Recovery will let you replace unhealthy resources with brand new healthy ones. Durable data storage is an important part of planning your cloud resources. Replicating your data to other sites or resources will protect its availability and integrity. There's three ways you can replicate your data: synchronously, asynchronously, or quorum-based. Synchronous replication ensures that your data has been durably stored on both the primary and replication locations. Any write operation will only be acknowledged as complete when this has taken place. This should only be used on low latency network connections where absolutely necessary to try to ensure maximum performance. Asynchronous replication decouples the primary node from the replica so that a write operation doesn't have to wait for any acknowledgement. This can introduce a replication lag but does not impact performance. And from personal experience, I've seen the difference between synchronous and asynchronous replication changing performance as much as 100%. Quorum-based replication is a mix of both synchronous and asynchronous replication. Replication to multiple nodes is controlled by defining the minimum number of nodes that must participate in a successful write operation. So if you have a cluster of 4 replicas, you can say, I need confirmation from at least 2 of them before the acknowledgement is sent back to the end user. A traditional data center failover scenario involves failing over all your resources to a secondary distant data center. Because of the long distances between the 2 data centers, synchronous replication is often impractical, slow, and usually involves data loss and isn't tested very often. However, it does protect against low probability scenarios such as a natural disaster. So if your main data center was in New York and your secondary was in, say, Washington, if New York had a massive outage, you could fail over to Washington, but it's going to be slow and practical and take some time. A more likely scenario is a shorter interruption in your data center, which isn't predicted to be too long. In this situation, your choice is to sit it out and wait, or initiate the complex failover procedure. AWS data centers are configured to provide multiple availability zones in a region, with low latency network connectivity. This means you can replicate your data across data centers in a synchronous manner, and as a result, failover becomes much simpler. Also, this concept is baked into many AWS services, such as RDS and S3. Active redundancy is great for disaster recovery situations or balancing traffic, but what if all the requests to your resources were harmful? For example, if a particular request caused a bug and it resulted in multiple instances crashing. A practice called shuffle sharding means only sending some of the requests to some of your resources. This way, if one shard of resources is infected or down, the other shard of resources will be up and running. In the example shown here, if request 2 is bad, then at least one set of resources is still protected. AWS economies of scale offer organizations huge opportunities to make cost savings. By making further use of AWS capabilities, there's even more scope to create cost-optimized cloud architectures. Right-sizing is one such approach. In stark contrast to traditional IT infrastructure, cloud computing means you can select the most cost-effective resource and configuration to fit your requirements. EC2, RDS, Redshift and Elasticsearch give you a wide variety of instance types to choose from. Through benchmarking, you can determine the optimal configuration for your workload. In some cases, it might be optimal to select many of the cheapest instance type available. In others, it might be more beneficial to select fewer instances but of a larger instance type. AWS Storage offers the same level of right-sizing opportunities. Amazon S3 offers many different storage classes to suit your needs. EBS also comes in a variety of different volume types, all of which will be covered in later lessons. AWS offers many elasticity options to help you save money. You can auto-scale your EC2 workloads horizontally or vertically. You can turn off production workloads when you don't need them. And where possible, you can use Lambda compute workloads so you never have to pay for idle resources. EC2 on-demand instance pricing means you only pay for what you use with no long-term commitments. However, there are two more ways to pay for EC2 instances. One of these is reserved capacity. By committing to a defined period of between 12 to 36 months, you can receive significantly discounted hourly rates compared to on-demand pricing. AWS Trusted Advisor, or AWS EC2 usage reports, identified the resources that would benefit from reserved capacity. There is technically no difference between on-demand and reserved instances. The only difference is the way you pay for it. This concept also exists for Redshift, RDS, DynamoDB, and CloudFront. EC2 spot instances are ideal for workloads that have flexible start and end times, as you are allowed to bid on spare EC2 computing capacity, and spot instances are often available at significant discounts compared to on-demand pricing. Your EC2 spot instance is launched when your bid exceeds the current spot market price, and it will continue to run until either you terminate it or the spot market price exceeds your bid. When the latter happens, your instance is terminated, and you'll not be charged for the partial hour that it was running. So there's three strategies to use for spot instances. There's the one we've just discussed, which is bidding. You could bid much higher than the spot market price for as long as the instance runs. This way, even if the market price spikes occasionally, you'll still make a saving overall. The mix strategy. AWS recommends designing applications that use a mixture of reserved, on-demand, and spot instances. This way you can combine predictable capacity with opportunistic access to cheaper additional compute resources. And then finally, there's spot blocks. AWS allows you to bid for fixed duration spot instances. These have a different hourly pricing, but allow you to define a duration requirement. If your bid is accepted, your instance will run until you terminate it or the duration ends. Now let's take a look at caching. Caching data means storing previously calculated data for future use, so you don't have to recalculate it again. There's two approaches. Application caching. You can design applications to store and retrieve information from fast managed in-memory caches. This way an application can look for results in the cache first, and if the data isn't there, it can then calculate it or retrieve the data and store it in the cache for subsequent requests. This approach improves user response times and reduces load on your resources. An example of this is Amazon Elasticache, which is a service that provides an in-memory cache in the cloud suitable for use with web services. Edge caching uses Amazon CloudFront, so you can cache static content such as images or video and dynamic content such as live video around the world using edge locations. This way users can be served the content that is closest to them, and resulting in low latency response times. The principle applies to both download and upload with edge caching. And finally, security. It's important to have security built into your plans and designs for AWS infrastructure. AWS allows you to take most of the security tools and techniques that you already know and improve them by formalizing security control design into your AWS platform. This simplifies the system for administrators and auditors alike. Now, we're not going to cover too much here because this is all covered in the IAM lesson, but there's things like defense in depth, which allows you to add multiple layers of protection to your resources. reduced privileged access to only give people the access they require. Security as a code lets you capture security requirements in one script that you can use to deploy new environments. And real-time auditing. AWS has multiple services to ensure you can test and audit your environment in real time.